Hey everyone, Stack Lessons here. Cost optimization patterns across all Amazon Web Services data services trips up a lot of students, so today we're going to make it crystal clear. Let's go. A team queried 10 terabytes of JSON logs in Athena every single day. Their monthly bill came back at $30,000. 3 engineering changes later, that same workload cost under $2 a day. Same data, same queries, just different knobs. By the end of this video, you'll know where those knobs stored across every Amazon Web Services data service and how to pick the cheapest one from the workload shape alone. Here's the core idea. Every Amazon Web Services data service has a pricing dial built into it. Glue has an execution class. Redshift has a capacity model. S3 has storage classes. DynamoDB has billing modes. Each dial has a cheap setting and an expensive setting, and the right choice depends entirely on the shape of your workload. Most teams pick a dial once and never touch it again, which is exactly how the $30,000 bill happens. The skill we're building today is reading a workload and picking the right setting on the first try. 2 rules anchor everything. First, prefer serverless over managed over self-managed. When the workload is intermittent, serverless wins because you stop paying when it stops running. Second, right-sizing beats over-provisioning. Match the capacity to the actual demand instead of buying headroom you don't use. Hold these 2 rules in your head as we walk through each service. Look at the workload first. If it's intermittent or unpredictable, serverless wins. You pay only when running and there's no idle cost. Athena, Lambda, Glue, Redshift Serverless, and DynamoDB On Demand all fall on this side. If the workload is steady, 24/7, predictable, reserved capacity wins. You commit 1 or 3 years up front, and in exchange, you get the cheapest per-hour rate available. Redshift reserved nodes, DynamoDB reserved capacity, and compute savings plans all sit on this side. Here's the map for the rest of the video. Glue has flex execution. Redshift has serverless and reserved nodes. Athena has the parquet, partition, and compressed triangle. S3 has lifecycle policies and intelligent tiering. DynamoDB has on-demand versus provisioned. EMR has spot on task nodes. And Lambda has memory tuning and a RM layered on top of all of them. Reserved capacity is the cross-cutting pattern for steady baselines. Learn these 7 knobs, and you'll answer most cost questions correctly. Standard Glue extract, transform, load runs on dedicated DPUs at $0.44 per DPU hour. Flex execution runs the exact same job on spare Amazon Web Services capacity for $0.29, up to 34% cheaper. The trade-off is start time. With Flex, Glue waits until spare capacity is available, so your job might start in 2 minutes or in 20. We met Flex briefly back in the Glue ecosystem episode. Today it's the go-to answer whenever a cost question mentions Glue. Amazon Web Services puts it plainly. Flex is for pre-production, test, and non-urgent data integration workloads, with up to 34% savings, running on spare compute capacity instead of dedicated hardware. Notice the 3 keywords: pre-production, test, non-urgent. If a scenario uses any of those words alongside Glue, Flex is the right call. Think of Flex like flying standby. You get a cheaper seat, but only when the airline has one to spare. For an urgent business trip, you'd never risk it. For a vacation flight that can leave a few hours later, the savings are great. Same logic with Glue jobs. Nightly backfills and test runs are perfect for Flex. A pipeline blocking a real-time dashboard is not. Here's the trap that catches people. Glue does not run on EC2, it runs on its own unit, the DPU or data processing unit. That means you cannot apply Spot Instances to a Glue job. If you see an answer that says reduce Glue cost with Spot Instances, that's the wrong mental model. Flex is the glue-native cost lever, and it's the only one. Redshift gives you a clean fork in the road. Start with the usage pattern. If the workload is intermittent or spiky, analysts running a few hours a day, BI bursts in the morning, Redshift Serverless wins. You pay per RPU second, and when no queries are running, you pay nothing. If the workload is steady, 24/7 with a predictable baseline, reserved nodes win. A 1 or 3 year commit gets you up to 75% off on demand. And as a bonus on the provision side, concurrency scaling credits give you free burst capacity for occasional spikes, which we covered back in the Redshift deep dive. Redshift reserved nodes can save up to 75% over on demand, in exchange for a 1 or 3 year commitment on a steady baseline. 2 things to know about that number. First, the 75% figure is the 3-year all-upfront option. The 1-year no-upfront discount is closer to 20%. Second, the reservation is tied to a region and a node type. If you resize the cluster or move to a different instance family, you lose the discount. One important nuance on serverless. Billing is per second in RPU hours, but with a 60-second minimum charge applied to each active compute period, not to each individual query. So when your workgroup spins up to serve traffic, you're paying for at least 60 seconds of base RPU capacity for that session, even if the actual work finishes in 2 seconds. For steady workloads that keep compute warm, this is a non-issue. But for bursty patterns, compute waking up, running a handful of tiny queries, then going idle over and over, you can rack up a lot of those 60-second floors. In that specific shape, a small provision cluster can actually be cheaper than serverless. Before we get to the Athena cost triangle, there's one separate lever worth calling out. Bytes scanned cutoff per query. 3 knobs reduce bytes scanned, and we'll see those next. This one is different. It's a hard ceiling on a single query. It caps a single runaway query before it drains the budget. So if someone writes a select star against a 10 terabyte table by accident, this setting kills the query before it spends $50. 3 knobs for the steady state, 1 guardrail for the worst case. Here's the cost optimization triangle. Parquet at the top, columnar storage lets Athena read only the columns the query asks for. Partition at the bottom left, folder-style prefixes let Athena skip entire date ranges without reading them. Compress at the bottom right, snappy or gzip means fewer bytes per file. All 3 independently reduce bytes scanned, and combined they compound. Layered on top of that, the byte scanned cutoff per query setting acts as a guardrail, a workgroup setting that cancels any query that would scan more than your configured limit. If you have to pick one optimization first, pick Parquet conversion. Practitioners consistently report that going from raw CSV or JSON to Parquet is a 10 times win on its own before you partition or compress anything. Then add partitioning, which is the second biggest lever. Compression and column selection are smaller refinements on top. Do them in that order so you get the biggest win immediately. Real numbers from a documented case on a 10 terabyte log dataset. Raw JSON scanned by daily queries costs about $30,000 a month. Convert to Parquet and that drops to roughly $3,000. Add date partitioning and it falls to about $200. Add snappy compression on top and the same workload comes in under $2 a month. That's over a 99.9% reduction entirely from reducing bytes scanned. On S3, the decision comes down to one question: do you know the access pattern in advance? If yes, use a lifecycle policy. You write calendar rules like move to infrequent access after 30 days, archive to Glacier after 90 days. Perfect for logs, backups, and compliance archives where you know the access curve. If you don't know the pattern, intelligent tiering watches access for you and moves objects between tiers automatically. The trade-off is a small per-object monitoring fee, which the lifecycle path doesn't charge. For data with unknown or changing access patterns, intelligent tiering is the right call. Notice the exact phrase, unknown or changing. Those are the keywords that map directly to exam wording. If a scenario says the access pattern is unpredictable or evolving, the answer is intelligent tiering. If it says move to infrequent access after 30 days, the answer is a lifecycle rule. DynamoDB On Demand is pay per request with no capacity planning, and it absorbs spikes automatically. Best for unpredictable, new, or spiky workloads. And after the November 2024 price cut, it's now the Amazon Web Services recommended default for most workloads. Provisioned plus auto-scaling is the other side. You set a baseline of read and write capacity units. Auto-scaling targets around 70% utilization, and it's cheaper than on-demand once sustained utilization climbs above roughly 35 to 40%. For the steady floor underneath that, you can layer reserved capacity on top for a deeper discount. Note the word default. Amazon Web Services now positions on-demand as the recommended starting point for most workloads, which is a meaningful shift from the older guidance that treated provisioned as the cost-optimal default. The reason is the 50% on-demand price cut from November 2024, which moved the break-even point up. Workloads that used to be definitely provisioned may now be cheaper on on-demand. On EMR, the cost decision is per node role. Master is the cluster coordinator, lose it and the whole cluster dies. So master goes on demand or reserved if you run clusters all the time. Core nodes run compute and store HDFS data. Lose a core node on Spot and you lose the HDFS blocks that lived on it. So core nodes also stay on demand. Task nodes only run compute, they hold no HDFS data, and losing one means no data loss. That makes task the safe place for Spot, where you can diversify across instance types and pull 60 to 80% off the compute bill. Here's the core idea in one sentence. If task nodes shut down because Spot pricing changed, no data is lost and the cluster keeps running. That's why task is the safe place for Spot, and why any answer that puts Spot on master or core is wrong, unless the scenario explicitly says the data is on S3 and there's nothing on HDFS to lose. Lambda has two charges. There's a flat fee of 20 cents per million invocations, usually negligible. The real charge is duration, allocated memory in gigabytes, multiplied by execution time in seconds, billed in 1 millisecond increments. The non-obvious part is that more memory also gives you more CPU at 1,769 megabytes. You get exactly one full vCPU. Below that, you get a fraction. Above, you get extra cores. That CPU with memory relationship is the whole basis for Lambda cost optimization. Here's the counterintuitive part. Adding memory often lowers your Lambda bill. The reason is that more memory comes with more CPU, so the function finishes proportionally faster. You pay more per millisecond, but for fewer milliseconds. Think of it like upgrading from a bicycle to a motorbike for a delivery job, higher cost per minute, but the trip takes a fifth of the time and your total bill drops. Here's a real example from Amazon Web Services documentation. An order processor tested at 4 memory settings: 256 megabytes, 512 megabytes, 1024 megabytes, and 2048 megabytes. At 256 megabytes, the function takes 400 milliseconds. That's our baseline cost. Double it to 512 megabytes and duration drops to 200 milliseconds, with total cost staying roughly flat. Bump up to 1024 megabytes and duration falls to 80 milliseconds. Total cost drops 22%, the sweet spot. Push further to 2048 megabytes and duration barely improves, now you're overpaying. The shape of this curve is exactly what Amazon Web Services Lambda power tuning is designed to find. 2 more Lambda wins worth knowing. Switching from x86 to a RM, the Graviton 2 architecture, is a one-line change in your function configuration and yields a flat 20% off duration cost. Practitioners call it free money. Amazon Web Services Lambda Power Tuning is the open-source tool that finds your cost-optimal memory setting by running the function at multiple memory sizes and graphing the curve. And recall from episode 21, provisioned concurrency only pays off above about 60% utilization. For spiky workloads, on-demand invocations stay cheaper. Step back for a second. Everything we just covered collapses into 2 shapes. Pattern 1, serverless or on-demand, wins when the workload is intermittent, spiky, or unpredictable. You pay only when you use it. Pattern 2, reserved or provisioned, wins when the workload is steady and runs around the clock. You commit to a baseline and get a deep discount on it. Every single knob we just walked through across all 7 services is one of these 2 shapes. The expensive mistake is matching the wrong shape to the workload. Keep that lens in mind as we get into the cross-cutting patterns and the traps. Here's a sharper version of the reserved versus on-demand call. The math is roughly the same across services. A 1-year reserved commitment typically discounts the baseline by 40 to 60%. That means if you're using the capacity more than about 30% of the time, reserved wins. Below that, on-demand wins. So when a scenario describes a workload, do the quick utilization estimate. 24/7 baseline means reserved every time. A few hours a day, a few days a week, on-demand or serverless. That single threshold drives the answer for Redshift, DynamoDB, and compute savings plans alike. 6 traps to watch for, and we'll move through them quickly. Glue plus Spot in any answer choice is always a distractor. Glue uses DPUs, not EC2. Redshift Serverless can actually be more expensive than provisioned for thousands of sub-second queries because of that 60-second minimum. Putting EMR core nodes on Spot risks HDFS data loss. Athena bills bytes scanned, not bytes returned. A select star with a limit 10 on a 1 terabyte table still scans the full terabyte. Reserved capacity bills even when idle, so overcommitment locks in spend with no refund. And intelligent tiering charges per object monitoring fees, which is a bad fit for buckets with millions of tiny files. Save this slide. It's the entire video compressed into a lookup table, the keyword on the left, the cost-effective service knob on the right. Non-urgent ETL points to Glue Flex. Intermittent analytics points to Redshift Serverless. 24/7 warehouse points to reserved nodes. Reduce Athena scan cost means Parquet plus partitioning plus compression. Unknown access pattern means intelligent tiering, while a known schedule means a lifecycle policy. Unpredictable DynamoDB workload means on-demand. EMR Spark cost reduction means Spot on task nodes only. And Lambda cost reduction means tune memory first, then move to a RM. When a scenario uses one of these phrases, the matching row is your answer. 7 things to lock in. Serverless beats managed beats self-managed for intermittent work. Reserved capacity wins for steady 24/7 baselines up to 75% off. Glue uses DPUs, so Flex is the cost lever, never Spot. Athena, Parquet, partitioning, compression, plus byte scan cutoff per query as a guardrail. S3, lifecycle for known patterns, intelligent tiering for unknown. EMR, Spot only on task nodes, never on master or core. Lambda, more memory often means lower cost, tune it, then switch to a RM. Now let's see how well that landed with 5 quick questions. Question 1. A data engineering team runs nightly Glue ETL jobs that process the previous day's clickstream data. The jobs are not time-sensitive, they can start anytime overnight. Which option is most cost-effective? Is it A, run the jobs on Glue with Spot Instances enabled? B, run the jobs on Glue with Flex Execution class? C, migrate the jobs to EMR with Spot Instances on core nodes? Or D, run the jobs on Lambda with provisioned concurrency? Take a moment to think. The answer is B. Glue Flex runs on spare AWS capacity for up to 34% off the standard rate, and it's purpose-built for non-urgent ETL. Option A is the classic trap. Glue uses DPUs, not EC2, so Spot Instances do not apply to Glue at all. Question 2. A retail analytics team runs SQL queries against a Redshift cluster only during business hours, roughly 8 hours a day, 5 days a week. The cluster is otherwise idle. Which option is most cost-effective? A. Redshift Serverless. B. Provisioned cluster with a 3-year reserved node commitment. C. Provisioned cluster with concurrency scaling enabled. Or D. Redshift Spectrum querying data in S3 Glacier. The answer is A. Redshift Serverless. You pay per RPU second only when queries run, so the 16 idle hours every day cost nothing. Reserved nodes only win for steady 24/7 baselines. For a business hours only pattern, they'd lock in spend you don't use. Question 3. A company runs daily Spark jobs on EMR processing data stored in S3 via EMRFS. They want to reduce cost. Which Spot strategy is correct? A. Use Spot instances on the master node. B. Use Spot instances on all core and task nodes. C. Use Spot instances on task nodes only with diversified instance types. Or D. Use Spot instances on master and task nodes on demand on core. The answer is C. Task nodes hold no HDFS data, so losing them to Spot reclamation causes no data loss. Master coordinates the cluster, Spot there kills everything. Core stores HDFS blocks, Spot there risks data loss. The safe pattern is on-demand master, on-demand core, Spot task with diversified instance types. Question 4. A team queries 10 terabytes of JSON application logs in S3 with Athena. Monthly Athena costs are over $20,000. They want to reduce cost with the smallest engineering effort first. What should they do first? A. Add a byte scan cutoff per query limit to the workgroup. B. Convert the JSON files to Parquet with snappy compression. C. Move the data to S3 Glacier Deep Archive. Or D. Replace Athena with a Redshift cluster. The answer is B. Converting raw JSON to Parquet is typically a 10 times cost reduction on its own, before you even add partitioning. It's the single biggest Athena cost lever and the right first move. Option A is a guardrail against runaway queries, not a reduction strategy. Glacier Deep Archive isn't queryable by Athena at all. Question 5. As covered earlier in this video, a team's Lambda function processes orders and they want to reduce per invocation cost. Profiling shows the function is CPU bound. Which change is most likely to lower their bill? A. Reduce the function's allocated memory to the minimum, 128 megabytes. B. Enable provisioned concurrency at 100% of peak traffic. C. Increase allocated memory to give the function more CPU, reducing duration. Or D. Switch the function trigger from a PI gateway to event bridge. The answer is C. Lambda allocates CPU in proportion to memory, 1 full vCPU at 1,769 megabytes. For a CPU-bound function, more memory means faster execution, and the duration savings usually outweigh the higher per millisecond rate. Option A would starve the function and increase total cost. Option B only helps if utilization stays above 60%, as we covered earlier in this video. And we're done with cost optimization patterns across all Amazon Web Services data services. If this saved you a wrong answer on exam day, hit subscribe, The Amazon Web Services Certified Data Engineer Associate keeps going, and I want you to pass on your first try. See you next time.